Discussing a Stanford seminar I attended yesterday about wide bandgap materials, high frequency power switching, and the potential for better power electronics. I think this really translates into a couple of things that are relevant for Tesla. One is wireless charging, the other is generally better power electronics equipment for the car, for the energy infrastructure that is needed for supercharging. Again, I already mentioned the wireless charging, which of course is important for the RoboCab situation. So there's a couple of things that really tangentially sort of pass by our position with Tesla related to this seminar. And I think I want to mention also for new listeners, the purpose of this podcast is to give people a sense of what it feels like to run a hedge fund. We're in the knowledge business, so we spend a lot of time doing various things that create knowledge. One is, let's say we attend seminars at Stanford. We're located very close to Stanford, so this is our go-to university. We do attend other conferences, even other universities when we have the potential to do that. But overall, we're mainly here at Stanford, sometimes at Berkeley. We go to conferences, we interview companies, we talk to entrepreneurs. So we try to do all kinds of things. We read a lot of books, a lot of journals, a lot of blogs, podcasts. So there's a vast variety of opportunity to learn about what we consider relevant. Now there's a little bit of a sort of a chicken and egg problem when it comes to, let's say, exploration versus exploitation. Maybe it's not chicken and egg, that's the wrong analogy, but there's this problem. Okay, we're on a certain track and we educate ourselves, let's say, about foundation models for robotics, and we've done a lot of work there, inspired by Sergey Levin and others, and sometimes it's okay also to do other things that might or might not have legs. And this is a good example. Like, this seminar is about power electronics, which is certainly not on top of our mind when it comes to investing in fundamentally new concepts, engineering practices. But then it turns out that some of the stuff that these people do, particularly the wide bandgap materials, actually could have huge potential for the future. And actually, it's also a good example of how engineering really can add value to a company and create wealth. Because if we can solve the material science problem that is associated with bandgap materials, such as, for example, gallium nitrate and others, we could really build new types of technologies that have huge potential for various applications. And I think it's sometimes also good to look at the value chain of academics and see, okay, like, what are these people actually doing? What is a PhD in electrical engineering doing these days? And are they on a path to create value that we think is interesting for us? Are they on a path to create value that is interesting for maybe other types of companies? Should we reevaluate our own investments based on what we see is going on in the science community? Because whatever is going on in the science community, for better or for worse, will translate sooner or later into technologies and entrepreneurial activities. This is another In-Run podcast. It's November 16, 2024. This is Krim Delco. For the year, we are up 56%. The market's up 23%. We're outperforming by 33%. So this seminar is about power electronics. It's part of a PhD class seminar at Stanford that talks about research projects and ideas that people who are attempting to do a PhD in electrical engineering could pursue. And I think it's a very interesting seminar for us because we're exactly sort of in that same boat as an investor. We look at potential ideas that maybe need a little bit more work now, but in the future could be really interesting for investing in entrepreneurial activities. And in this particular, by the way, links are in the show notes in terms of who and what and all that. I don't want to spend time here with names and things like that because I don't know these people, and it's not that important. What's important is really the big picture here. So we have wide bandgap materials such as gallium nitrate that have a certain property that semiconductor materials tend to have, but the ones that we use, the silicon-based materials, they are in certain ways much better, and in other ways they have flaws. And what wide bandgap materials have is they have a wide bandgap. What that means is that the band between conductor and not conductor is wider. When you have that, you can have much higher voltage, which means that you can do things with those materials that have a lot more juice. So you can move a lot more energy, let's say from A to B. You can store a lot more power. You can have much higher currents, which is, you know, all based on Ohm's law and things like that, relatively the same thing. And I don't want to go into technicalities here, but think about it this way. You have a certain material that by nature of what it is allows you to do more power with less surface area, with less material. So the material itself has properties that can solve certain problems, such as, for example, just size. You can have smaller devices that can store more power and move more power. And one of the things that they can do, and by the way, the reason they can do this is because they can switch at very high frequencies. And that's when you switch, when you build a converter, which is you convert from AC to DC, or DC to DC, or DC to AC. Whatever you're converting, you have to think about it this way. You have electricity, which is, let's say, generated somewhere. Let's say it's generated traditionally by a nuclear power plant or a gas power plant, and then goes to the grid. And that electricity flows at a certain frequency that might be very good for transmission, but is not necessarily good for what you need it for, which is, let's say, to charge an electric car battery. So what you need is a converter that converts that electricity into the kind of electricity that is good to move the electrons into your battery. And that's what a converter is there for. And the higher you can do the switching, the faster you can do it, and the more power you can move in less time and on less surface area. So you save yourself money, time, efficiency, all of these things. The downside is, for example, thermal conductivity is sometimes better, sometimes worse. But the problem is when you move large power type situations, so when you move a lot of power on a small surface area, things can heat up very quickly, which is one of the problems, let's say, of fast charging. But the thing that caught my eye in this presentation was particularly the discussion about wireless charging. Now, the problem with wireless charging from a big picture perspective is that it's possible in principle, and it requires innovations on the switching side, so on semiconductors, and innovations on the inductor side, which is the kinds of materials that currents in magnetic fields interact with, so they can move power from one place to the other and store it also properly. So this is a material science problem. But what I thought was really interesting is that it seems to me, according to this professor, that in principle, this is possible. And what is required is an engineering solution. And this is really the kind of place where Musk excels, you know, because he is not necessarily in the business of science, right? He's not rediscovering science. But what he can do really well is take what's known and then move it forward on a trajectory towards more efficiency, lower cost, and higher scale. And that's really what he has been doing with Tesla and SpaceX, and what he's attempting to do with Neuralink and others. So this is really very promising. And I think for us as investors, it's very important to understand that, let's say, why is wireless charging important? Well, a Cybercab network of millions of cars requires some sort of wireless self-charging, because otherwise the human labor and the efficiency of charging could become a bottleneck. So because of that, we believe that wireless charging is actually a crucial part of the equation. And after this seminar, we are more convinced than before that it is in principle possible, because according to the professor himself, he says, look, I am a skeptic about this. I don't think that it's going to work because it's too expensive and too cumbersome. But he said himself, if you had asked me 20 years ago about iPhones or electric cars, I would have said the same thing. So in other words, when something is possible in principle, you can actually do it by doing the right scaling, the right engineering, the right entrepreneurial initiatives that people like Elon Musk are very good at. So this is, I think, hopefully this comes across, because it's really important for us as investors, and this is kind of where the rubber meets the road when you are in the business of wealth creation, is like, where can technology and science and entrepreneurial activity sort of, where's that Venn diagram that overlaps and really delivers the kind of value that we as Orange Capital Partners are hoping to achieve by investing in fundamentally new concepts in engineering practice. This is exactly the kind of place. Now, wireless charging on its own, of course, is not going to make or break Tesla, but it's an important piece of the puzzle. And according to the seminar, it is actually possible. In principle, it's possible. And this is really what matters. So to summarize, white bandgap materials, white bandgap semiconductors are one way to create more powerful power electronics, which is key to companies like Tesla. It's not going to make or break the company, but it's absolutely important for better power electronics, at least on the wireless charging side, which we believe is a crucial part in the Cybercab rollout. Thank you.